mic picking me up okay? Not too loud? All right. So, thank you for the introduction. Appreciate it. Try not to breathe. Okay. So calibration is the act of characterizing the behavior of a GNSS antenna. So this talk is going to concentrate on carrier phase calibrations of receiver antennas used at ground stations. We're not talking about satellites here. Calibration of those antennas is not equivalent to certification. And so the IGS, through its Antenna Committee, serves an important role in verifying the quality of antenna calibrations so that the highest quality product is achieved. So that calibration product is often referred to as IGS Antex. You know, it's corollary to the RINEX we're all familiar with. Antex stands for Antenna Exchange Format. The Antex file contains models for the total phase center correction, or PCC. I'm going to try using the pointer here. Oh wow, there's a bias to that. Okay, so phase center correction, or PCC. And let's see. So that's the correction that we all apply when we apply antenna calibrations in our GNSS processing. But the Antex format decomposes that PCC into two different components. So the phase center offset, or PCO, is one of those components, and the other component is PCV, or phase center variations. So you're going to hear me toss around PCC, PCV, and PCO throughout this talk. So this talk presents early results from the IGS calibration and validation campaign, where antennas were circulated in a ring around the globe. We provide an overview of the campaign, which had multiple goals, which I list on this slide. To meet those goals, the campaign organizers developed new software and equations for analyzing results. I'll share early results from using this new software and metrics we devised on data collected in this campaign. So over the history of absolute antenna calibrations at IGS, a company called Geo++ has been the most significant contributor to the Antex file maintained by IGS. In the previous decade, agencies such as Geoscience Australia, IFA, and Unibond have also contributed calibrations. And in the last few years, several other agencies have built additional facilities and expressed interest in contributing to the IGS. So this collaboration brought together 9 different agencies across the globe to compare their results. My thanks go out to all these groups for your efforts in calibrating antennas and freely providing the results. Oh goodness, this thing drives me crazy. Okay. 7 of the participating facilities used a variety of robots in outdoor environments, whereas 2 of the facilities operated anechoic chambers. It's worth noting that several of the facilities operate Shunk-branded robots and calibration software sold by Geo++. These facilities, denoted with the little cyan diamond shape, are allowed to provide calibrations to the IGS as a matter of routine due to this mounting equipment. We note that important differences exist between the facilities with this equipment, such as analysis software, GNSS receivers, and of course, the field environments are going to be different as well. Sorry, trying to go back. And I found the back button. Okay, and the forward button, great. So 6 individual antennas were provided by participants for the calibration. In this campaign, we calibrated all of the antennas without radomes, even if that model was present in the IGS network with a radome model. So for example, the Hartson antenna in the lower left-hand corner is only present in the IGS network with a radome, but we're looking at the unradome case here. We decided to ignore radomes to ease the process and remove a variable that might introduce some inconsistency. But the models chosen represent typical antenna models and types present in the IGS network today. The green shapes give the percentage of IGS stations with that category of antenna. Yeah, I appreciate that. Okay. Thank you, I appreciate it. Okay, so circulation antennas began almost 2 years ago, and the testing is nearly complete. So this graphic shows results availability as about a week ago when we completed these initial results. So 3 antennas are currently at DLR for testing, and Geoscience Australia and Unibond are awaiting the last antennas in the circulation plan. So preliminary analysis showed that DLR results need to be reanalyzed, so that's why we indicate them with a lighter color, and their early results are not included in this study. But all the calibrations that you see marked in dark green are included in the analysis you'll see here today. So in the past, we've often assessed calibrations in terms of their spatial PCC, total phase center variation, total phase center correction, kind of spatial differences. So as you can see with these stereographic plots, it can be difficult to take this spatial variation and assess the meaning of those differences with this kind of traditional approach. We've therefore devised some new metrics for comparison and assessment, which allow analysis in a geodetically meaningful way that also enforces consistency of the results. So I'll go through some of those advances in these next few slides. Often a comparison of PCO values is desirable, and something we have a tendency to do in this community, because PCO represents the mean phase center of the GNSS observation. So I note that although it can be instructive to view calibrations in terms of those component PCO and PCV, the separation between those two components is completely arbitrary. And thus the total PCC is what is applied in positioning software and what we should really be looking at. But if we want to look at PCOs, here's a way to do it. Our study developed a robust method to separate PCO from PCC so that we can compare those values consistently. So on the left, we show the PCOs taken directly from participants' data submissions, or their Antex files, for one of the antennas that we studied. And on the right, we show the same results after we have solved again for new PCOs in a consistent manner. So you can see on the right-hand plot that the degree of agreement between all these different techniques is much easier to observe. Another advance is the development of a metric which summarizes the differences between two total calibrations, two total PCCs, as a single quantity. So we call this the scalar delta PCC or scalar metric. In the formulation shown here, the spatial variation in PCC is compressed into a single value. Found it. There's the single value. And here's the total PCC difference. So when this metric is applied to two calibrations that have the same phase center variations, it ends up giving the distance between their phase centers. So this scalar metric is something we express in length units. This metric also has the quality of de-weighting data for low elevation angles, as is typical in GNSS processing. So in our study, we looked at the spread of these scalar values, or scalar metrics, for groups of antennas. The range represented uses a minimum and maximum value from a group of calibrations, and we only calculate this spread when we have 3 or more antennas in a group. I'll talk more about what these groups are in a later slide. So we're in a reference frame session, and I expect audience members will want to know the effect of calibration differences in the positioning domain. So we also simulated the impact of the delta PCC on the parameter domain. This simulation uses ionosphere-free dual frequency combinations for each satellite system. In the bar graphs, we're going to show expected change in north, east, and up components of position when using a specific individual calibration provided by one of the facilities. And that's going to be relative to this doing a solution using the IGS technique. So these are not position errors we're showing, rather than changes in position by changing your calibration table. So important in our study was understanding the degree of agreement or disagreement between different facilities and techniques. So for each antenna in our study, we classify the facilities into 2 groups. The first group are facilities that already contribute to the IGS today. These are facilities that appear in the IGS 20 Antex file that you could download today. We indicate this group using a tan color in the subsequent slides. The second group are going to be facilities which agree with each other within 2 millimeters on their vertical PCO component. We are going to indicate this group using a cyan color. The 2 groups are going to change from antenna sample to antenna sample and overlap to some degree, but you'll also see some consistency as we go on. Okay, so in these slides, they're all going to be laid out the same, but the results are going to change. And it's going to be 6 slides with same plots in the same places, but the antenna sample is going to change for each of the 6 that we analyzed. I already talked about the cyan color to indicate the 2 millimeter vertical PCO agreement, and the tan color to show you where we're talking about facilities that already contribute to the IGS. So for this Javad antenna, most facilities show a very close match in vertical PCO for the IGS type mean, which is always going to be shown as a red line in the left-hand plot. Position deviation showed that the antenna sample tested has a strong east component variation relative to the IGS type mean, and that this was detected and measured by all the facilities. Even with this close agreement, the spread in the scalar metric ranged 1 to 3 millimeters for all facilities. This second JPL-style choke ring antenna was measured by 8 facilities. 5 of them agree within 2 millimeters vertical PCO, as shown by the cyan band. It's interesting to notice that the 5 facilities with close agreement have a 1 to 3 millimeter spread in the scalar metric, whereas the 4 IGS facilities have a larger spread of up to 4.5 millimeters. This conical choke ring from Leica has a closer vertical PCO agreement with the IGS type mean. And as is the case with the previous antenna, the spread of the scalar metric is greater amongst the IGS facilities compared to the 5 facilities with the closest agreement. Only a few facilities have tested this Hartson antenna. I'm going to go past it a little quicker for sake of time. And then for this triple ground plane antenna, the frequency dependence of the range of the vertical PCO is quite small compared to antennas on the previous slides. And in the majority of cases, the individual calibrations are producing roughly the same positions as the type mean. We're unable to assess scalar metric for the IGS contributors because there were only 2 in this group to date. Okay, I'm in discussion, my apologies. Can I just quickly, due to my mic problems? Okay, so one thing is that early insights from this study are only possible due to major software development that has been undertaken by the organizers of this campaign. So we'll continue to expand the capabilities of the software with additional graphics and metrics, and we are developing code in multiple languages. So we invite our colleagues to help us with this open source coding effort. So in conclusion, this international collaboration among 9 different calibration facilities, although not yet complete, is leading to some important insights on the nature of antenna calibrations. We developed open source software for the calibration analysis that uses standardized algorithms to account for GNSS features. We've come to understand that the same antenna tested at different facilities will have calibrations that vary at the 1 to 4 millimeter level on each frequency study. And results to date demonstrate that groups currently contributing to the IGS Antex have more variability than we really previously appreciated. We also observed that several facilities show excellent agreement with each other and close agreement to the results of GEO++, the facility which has been the strongest contributor to the IGS Antex to date. So my colleagues and I hope you'll come by our poster to discuss detailed results where we provide additional plots from our analysis software. And we also invite you to join the Antenna Committee's winter meeting on Friday, where we'll provide recommendations for new contributors to IGS Antex and recruit colleagues to help with our open source software. All right, thank you for your patience.